Hi all. See this problem it came in the year 2018 which talks about that test for the differentiability at some particular points, right? Now see that why I say that particular point. See that the function it deals with that modulus function, sine function and exponential function. Now if I remove the mod function, right, then the function is obviously differentiable because there are no kind of discontinuity and all. So only the point we have to test for, that is x equal to pi and x equal to 0. Why? Because our mod function is mod x is actually changes shape or the pattern as x equal to 0 and that mod of x minus pi changes shape for that. So for solving that, we can apply the right limit left limit concept or right limit left right limit derivative concept to do that. But that actually very complicated here because the function is very difficult, right? So we'll use some tricks to solve that problem. Okay, so let's go ahead. Okay, now see that for this particular problem, our doubtful point or that where the function may not be discontinuous, right, that x equal to pi and x equal to 0. So let's write down that. We'll see that the function fx may or may not differentiable at x equal to 0 and x is equal to pi, except that for any point fx is differentiable. That's very obvious. Now, to find that test for that differentiability, we have to test for x equal to 0 point, right? So let's test that, right? So here we are testing the differentiability at x equal to 0. So test at x equal to 0. So that's why we'll consider the interval zero minus h, 0 plus h, and h is greater than 0, or sorry, h is tends to 0. So that's actually we are trying to calculate the right and left derivative in that interval, right? 0 minus h and all that stuff. So here there are two possibilities. One is x greater than 0 and x less than 0, right? So let's see that, okay? So that's it. Now see that when x is greater than 0, okay, the intuitive case is that x is less than pi, okay? That's obvious. Now, if I write down the function fx at this case, right, when x equal to greater than 0, then my fx will become x less than pi. So, therefore, it will be pi minus x. Then e to the power of x minus 1 and sine x. That's my function fx. Let's try to calculate the derivative. So the derivative f dash x will gives me that differentiation of first one, that is minus e to the power x minus 1 multiplied by sine x. Plus we have pi minus x, then we'll differentiate the second function, that is e to the power x and sine x. And then we need to do the sine x differentiation, therefore it's pi minus x e to the power x minus 1 and sine x will be cos x. That's it. Now let's substitute x equal to 0. So f dash 0 will gives me that, see, sine 0 and e to the power 0 minus 1 is 0. So therefore it's 0. That's why this gives me the right derivative at x equal to 0. Now, that's way we can calculate the right derivative instead of calculating that if limit x plus limit form, right? That if 0 minus k or 0 plus k minus f 0 divided by k, that formula, right? We all know that. So using that, except that limit formula, we can also calculate based on that. Only the difference is that, see that here we are evaluating the function in the neighborhood of 0, right? So what the function value behaves in that interval, we only consider that function. So we need to calculate also the case when x is less than 0 to calculate the left derivative. So therefore say kx less than 0. Therefore it is obvious that x is also less than pi. That's the intuitive condition. So therefore see that here fx First function is mod of x minus pi, x less than pi, that is becomes pi minus x, e to the power x or e to the power minus x minus 1, and we have sine of minus x. So therefore this function can easily be written as pi minus x multiplied by e to the power x minus 1 multiplied by sine x with a minus sign. Now let's differentiate it. So f dash x. So f dash x becomes like, let's derivative of minus of minus 1 and e to the power minus x minus 1 into sine x. Go ahead, we'll write that minus of pi minus x minus e to the power minus x sine x, and then we have minus of pi minus x e to the power minus x minus 1 and cos x. Now also, if I substitute f x equal to 0, we'll say that that's equal to 0 because sine 0, here e to the power 0, 1 minus 0. So that gives me the left derivative. So therefore, we'll say that as right derivative and left derivative are equal, so therefore we'll say that the function f dash x exists at x is equal to 0. That's it. So we have proved that the function is differentiable at x equal to 0. Now we have to test that at pi, right? Because 0 is already tested and we proved that. So let's go ahead and understand the function at x equal to pi plus pi h minus pi h. So let's consider that. So here we'll consider that now we'll test x is equal to pi. So therefore we consider the interval pi minus h and pi plus h where h tends to 0. That's it. So therefore, this point we need to calculate. Okay. Now see that when we have that pi plus h, that means we need to consider the condition where x is greater than pi, x is less than pi. Okay. Let's see that. So if I consider the condition that x is greater than pi, so that means the intuitive condition is that x is greater than 0. In that case, my function fx is obviously equal to x minus pi, e to the power x minus 1 and sine x. Let's differentiate it, okay? So f dash x will give me that 1 into e to the power x minus 1 sine x. The next term will be gives me that x minus pi e to the power x and sine x plus x minus pi e to the power x minus 1 and cos x. Now see that here if I substitute f dash equal to f dash 0, right, we'll get that as sine 0 and this is e to the power 0 minus 1. Again it's 0. So therefore this gives me the right derivative at x is equal to pi. Let's go ahead and test it for x less than pi. And here we have that x greater than 0 as well. So therefore, in that case, basically we are taking that pi minus h, pi plus h. So here taking that value as x less than pi means that inside that interval. So we cannot ignore that interval. Now see that again. Here we can say that fx, so the next line that x less than pi. So mod of that will change to pi minus x and remaining all will be as it is. So e to the power x minus 1 and sine x. Let's derivative it again. So therefore we can say that f dash x here will gives me that minus e to the power x minus 1 sine x plus pi minus x e to the power x sine x, and the last one obviously we have that as plus pi minus x e to the power x minus 1 and cos x. Now here we can apply that x equal to 0. So f dash 0 will gives you sine 0, this is 0 again. So that is gives me the left derivative at x equal to pi. So left and right derivative are equal, so we'll say that f dash pi exist. So here I just write two wrong thing. Here that should be pi because we are testing at pi. Wrongly I write that pi. Now see that here if I substitute pi, we can get that again it's 0 because if I substitute pi, this is sine pi 0, x minus pi is 0, so there is not an issue. If I substitute pi here, this last one 0, this two are by sine it is 0. So therefore f dash pi exists, right? So both cases we can say that f dash pi and f dash 0 are existed, right? And we already say that, right, that function may not be discontinuous, not differentiable at 0 and pi, except all other point it is definitely differentiable. So that's why, right, we can say that the set is an empty set because we are not having a point where the function is not differentiable. So therefore that set is becoming empty. So that's why that's the option, right? So here we don't use that right and left limit derivative concept directly. We just use it in a different way. In the only logic is that it is an MCQ type problem, and obviously that if I trying to apply the limits directly, it becomes a huge problem. So to eliminate that, we just go ahead with the small tricks. I think you understood it. Thank you.